Hi, welcome to the final part of the semester review video. This first question here is asking us about the domain and range of the square root function to the right. This graph that you're seeing here, this is a square root graph or function. And so it's just asking for the domain and range. So as a reminder, domain represents the x values from left to right. And the range represents the y values from bottom to top. So starting with the domain, looking from left to right, if I were to take my pencil, pretend this is your pencil, and move my pencil from left to right, what is our first point that we see? Boom, right there. Our first point on the x-axis starts at -4. Now this is a closed circle, so we use a bracket. And as we continue to the right, where is our graph heading? We see an arrow, so we know we're going towards infinity. Now, when looking at the range, we do the same thing from the bottom. So starting from the bottom, what is the first point we see here? It is it is right here on the x-axis. So we're not looking at the x-axis numbers anymore, we're looking at the y-axis numbers. So our graph begins right at the center at 0. And as we continue up, our highest point that we can see here, yes, it looks like it's at 3, but at 3, we have an arrow again. So we're going towards infinity with a parentheses. Now, the reason we use parentheses for infinity and a bracket for a close point is because infinity is not a tangible number. We can't actually count to infinity, so it's just kind of an estimation. This graph goes on forever. So to expand on that, the parentheses means an estimation, and the bracket means more of a concrete, a hard point. All right, next section here, we're looking into exponential and logs. It says graph the exponential function. State the domain and range in interval notation and horizontal asymptote of the function. Graph in your calculator to check your answer. Okay, we're not even going to bother checking our work. We're just going to do it. So anytime we graph something, we need to identify A, H, and K. As a reminder, even in the exponential graph or function, we have the same looking formula, I guess. X minus H. Okay. So really all we're looking for is A, H, and K. These numbers will tell us where we're moving. As a reminder, which we've talked about in the last two videos, A either represents a vertical stretch or a vertical compression. It represents a stretch if it is greater than 1, a compression if it's less than 1. H goes either left or right, but we remember that X lies. So it's always opposite of what we see it as. K goes up or down. So let's take a look here at our function here. So our base, let's look back at our formula. Our base is 2. So that 2 is not going to, it's not going to change where our graph goes. So what we're looking at is this negative in front, this plus 3, and this plus 4. The negative in front, we like to think of it as separate from the A value because the negative represents a reflection. So it isn't necessarily A. We don't have an A here, it's just a 1. But the negative does represent a reflection over the x-axis. The H here represents a movement left or right, and it says it's positive 3, but we know that x lies, so it is actually negative 3. And that means we're going down And lastly, k is a positive 4. Oops, okay, let's go back. I'm so sorry. I just said h goes left or right, and then I said let's go down. No, it's going to the left. And 4 is positive. This is the one that goes up. All right, so we need to identify the parent function so that we can get the parent table, and then the transform table, we will add or subtract h to x, and we will multiply y by a, and add or subtract k. So let's look back at our function here. Everything that I highlighted is something that we were already focusing on, something that we're already using. So the only thing that's left is our base to the x. So our parent function here is 2 to the x. Now, in order for us to get the points of that parent function, all we need to do is plug in these x values into x. So we're going to have 2 to the negative 1, 2 to the 0, 2 to the 1, and 2 squared. Now, calculating this, anything to a negative number is going to be flipped. So instead of 2, we have 1/2. Now 2 to the 0, anything to the 0 is 1. 2 to the 1 is just 2, and 2 squared is 4. Now the transform table, we're going to take these values and transform them using the numbers from our function up here. So x, we're taking these x values here, and we're adding or subtracting h. We said h is negative 3. So we are going to subtract 3 from all the x values. And then for y, or f of x, we're going to multiply, even though our a is a positive 1, we're going to multiply by that negative so that we get that reflection going. And add 4. That's our k value. Okay. So looking at these x values here, we're going to subtract 3 from each of them. Negative 1 minus 3. Let's do it this way. Minus 3 is going to give us negative 4. 0 minus 3 is negative 3. Negative 1 minus 3, negative 2. And 2 minus 3 is negative 1. All right, now we're going to take the y values. We're multiplying by a negative, and then we are adding 4. So 1/2 times a negative 1 is negative 1/2, plus 4 is 3.5. 3.5. All right, negative 1 plus 4 is 3. Negative 2 plus 4 is 2. And negative 4 plus 4 is 0. Now we have our new points, or let's explain it this way. This table are the points of this graph right here. So we're going to graph our new graph. We have negative 4, 3.5. Negative 3, 3. Negative 2, 2. Negative 1, 0. So our graph is like this. All right, and just for good measure, let's take a look at what our original graph looked like. This is negative 1, negative 1/2. 0, 1, 1, 2. Okay, these are kind of getting crooked because I'm not looking at them exactly. 1, 2, and 2, 4. Why are these so perfect? Negative 1, negative 1/2. Oh, okay. Let's see what I did. Not negative. I was looking at that negative in front. It's still positive 1/2. There we go. Okay, let's actually check our work because mine is weird. Sure, it's right. still. All right. Oh, did I do this already? No. But I did have one ready, so we're just going to fix it. Say negative 2x plus 3, I think it was, and plus 4. X plus 3 plus 4, okay. Come back at our Desmos. That's our graph. Nice. All right. So we can also draw our asymptotes. The asymptote of this graph right here is, I probably drew my line too high, but it's right here at 4. And the asymptote of the original graph is, or the parent function, is at 0. So our new asymptote is going through the y-axis at 4. It also matches k. The transformations, we wrote them at the top. We said reflection over x-axis, left 3, and up. Domain and range. We're talking about of the new function, not the purple one. So new function, domain and range, from left to right. Looking at x values. From left to right. Our furthest left x value is coming from an arrow, so negative infinity. And as we increase, it looks like our graph is going, and the asymptote is horizontal, so no, it's going towards positive infinity. And the range, from the bottom as we go up, what is our lowest point? We hit that arrow. Our range is coming from negative infinity, and our graph is going up towards that asymptote where our graph will never touch, never cross. It is at 4. And just to make this a little more accurate, and fix this line right here. There we go. Now it's a little more accurate. Okay, so let's go ahead and continue to the next one. Now we're going to be graphing the log function. So same idea. Let's go ahead and get started. We need to start with identifying the parent function of the log. Anytime we identify the parent function, it is just the log, the base, and an x. That's it. Log, base, x. So when we graph logs, we need to use its inverse, which is this exponential parent function. We need to use the inverse of it in order to find our points. So the inverse, how do we find the inverse of a log? Well, we look at the base and we raise it to the x. So we have the base on the log becomes the base of the exponent. Now these numbers here are going to be plugged in for x, just like we did in the last problem. So 3 to the negative 1 is 1/3. 3 to the 0 is 1. 3 to the 1 is 3. And 3 squared is 9. Now, the parent table of the log function is the inverse of what we just found. So we need to swap those x and y values. All right, now to transform, we need our a, h, and k. So we're looking in front of the log, there's nothing there, so a is 1, which means no change. Now right here, that's our h value. Okay, h, k. So our h, remember x lies. So h is positive 1, which means we are moving to the right. K is positive 2, which means we are moving up. Now, again, our transform table, we're going to take these x values that we just found. We're going to add or subtract h. Y gets multiplied by a and add or subtract k. This works for all graphs, no matter what kind of graph you're using. You can identify a, h, and k. You can take your original parent table points and do this little plus or minus h, and then the same thing with the f of x to find your new points. Okay, so let's take our x values here, plus or minus h. What is our h? Our h is positive 1. So we're saying this, plus 1, plus 1, plus 1, plus 1. And then the f of x, our a is 1, so multiplying by 1 is not going to change anything. So we're not going to bother writing times 1. But we do want to say plus 2. We're going to add 2 to all of these numbers here. And let's calculate. So we have 1/3 plus 1, that's 1 and 1/3. 1 plus 1 is 2, 3 and 1 is 4, 9 and 1 is 10. Now for the f of x or y, we have negative 1 plus 2, so 1. 0 plus 2 is 2, 1 and 2 is 3, 2 and 2 is 4. Now let's go ahead and graph our new table. So we have 1 and 1/3 and 1. Then we have 2, 2, 4, 3, and 10, 4. All right, connecting these dots now, we do have a vertical asymptote right where our graph begins. Our point is right after positive 1, so our vertical asymptote is going to be right there at the positive 1. Our vertical asymptote of the log will always match your h value as well. So our vertical asymptote is going through the x-axis at positive 1. And look at your h value, positive 1. Think back to the exponential graph we just graphed. The asymptote, the horizontal asymptote, matched the k value, which is 4. So kind of cool. Let's go ahead and graph the original function as well, just to show. We got 1/3, negative 1, 1, 0, 3, 1, and 9, 2. And as you can see, this graph was moved to the right 1 and up 2. Woo! So the transformations, we just said we went right 1 and up 2. Domain x values from left to right. What is our furthest left x value? It's that asymptote of 1. And as we go to the right, our graph is continuous, infinitely continuous towards infinity. Our range, we start from the bottom. We see that arrow, so it ends at negative infinity. As we go up, we see that arrow again. And although it looks like it's pointing to the right, it is going to the right, but it is microscopically moving upwards as well, up towards infinity. All right. Now, you might be wondering, why are we using parentheses on both the number and the infinity? Again, because these numbers are estimations. They're asymptotes. Our asymptote is at 1. What is an asymptote? An asymptote is an invisible line or an invisible barrier that our graph comes really close to, but will never actually touch, never actually cross. So we get really close to that 1. See how close our line is to 1? Our line is actually never going to actually touch 1. Okay. Properties of polynomials. Use the graph of the polynomial to answer the following. Is this even or odd? Something we talked about in class was that even is when the two hands or the ends of the polynomial are facing the same direction. Odd is when they're facing opposite directions. So if we were to imagine our polynomial as having like two hands here, it has its right hand up and its left hand down. So because the hands are facing in different directions, this is an odd polynomial. And what does that mean to us? Well, if the polynomial is odd, that means the degree, or the highest term, is going to be an odd number. We're not there yet, but we'll get there, and I'll show you it is an odd number. All right, next we have our positive or negative leading coefficient. So when we look at the leading coefficient, we're looking at the right hand. And the right hand of this polynomial is facing up, which is a positive direction. So we're going to have a positive leading coefficient. Now, looking at the degree again, we talked about this yesterday in our video. I said that we can count the degree by counting the curves and adding 1. Or count the direction. So if we start from the bottom, obviously the curves plus 1, that's 1, 2, so our degree is 3, or we can count the direction, 1, 2, 3. Our degree here is 3. And just like I said, it is an odd number. End behaviors, we're looking at the end. As x approaches negative infinity, right here, to the left, where is our graph going? We look at our graph, and our graph is going down towards the negative numbers, which means it's going towards negative infinity. And as x approaches the positive infinity to the right, what is our graph doing? Our graph is going up towards positive numbers, so towards positive infinity. All right, use the fundamental theorem of algebra to determine the maximum number of solutions in the polynomial. So fundamental theorem of algebra tells us that the maximum number of solutions in a polynomial can be found by looking at the degree. And let's talk about the degree again. What is a degree? Degree is the highest exponent. So even if the polynomial is not in standard form, which means highest to lowest exponent, we need to find the highest. It's not the first. It's not the first one. It's the largest, the highest number that we have as an exponent. So here our highest, let's just look at all of our exponents. We got 5, we got 1, we got 2, and we got 7. Which number is the highest? 7. So that means we have 7 possible solutions. All right. Again, maximum number of solutions, we need to look at the degree. What is our degree here? We got 6, we got 5, we got 1, and we have no x. So what's the highest number here? 6. 6 possible solutions. All right, 7.7, factoring cubic and quartics. Factor using the sum of cubes formula, or over here to the right, the difference of cubes formula. Let's write those out really quick. The sum of cubes formula is, I don't want to tell you wrong, so let me look it up. If you start with a cubed plus b cubed, the formula, the factors would be a plus b times a squared minus a times b plus b squared. Now the difference of cubes formula if we started out with a cubed minus b cubed, let's also talk about that really quick. Difference literally means subtraction. Sum literally means addition. So how do we tell the difference? We look at the sign. Are they subtracting or are they adding? So difference of cubes, we have a cubed minus b cubed. That's what we start with, and we can factor that into a minus b times a squared plus a times b plus b squared. All right, so let's use this formula starting with the sum of cubes. Let's just do the sums first, and then we'll go back and do the difference next. So sum of cubes. We're starting out with this right here. We have a cubed plus b cubed. So a cubed is x cubed, and b cubed is 125. But our factors need a, b, a squared, b squared, and a times b. We need all these numbers, so we need to figure out what a is alone without it being cubed. So how do we get rid of the cube? We cube root. So a is just x. The cubed root of x cubed is x. And the cube root of 125 is 5. So that means b is 5. Now, our formula also asks for a squared. So if we were to square a, which is x, we would get x squared. If we were to square b, we would get 5 squared, which is 25. The last thing we need is right here in the middle, a times b. So we're looking at a right here and b right here. What's x times 5? 5x. So we're going to use all these numbers to write our formula out nice and pretty just the way it asks for, or just the way the formula calls for right here. So starting with a plus b. A is x, b is 5. A squared is x squared minus a times b, so minus 5x plus b squared, so 25. Easy enough, that's it. And now we have factored the sum of cubes. Okay, next, sum of cubes again. I need to see that formula so I don't get it wrong. On the test, you will be given the formula. So I told you I'd never expect you to memorize it, and here we are, not expecting you to memorize it. All right, sum of cubes. This is a little different because we have this coefficient in front of x cubed, but it doesn't change what we do for it at all. We're going to do exactly the same. So we're starting out with cubing both terms. And when we cube 27, we get 3. So let me write this out. A equals 3. And when we cube the x, we get, or sorry, when we cube x cubed, we get x. Then b, when we cube 8, we get 2. Now let's see, what would a be if I squared it? Well, if I squared it, I'd have 3 squared times x squared. And 3 squared, sorry guys, 3 squared is 9. And x squared is just x squared. All right. So moving on to the b. B squared is just 2 squared. And what is 2 squared? It's 4. And then last I need a times b, which is just a, 3x times 2 is 6x. Okay, a lot of little writing here, but don't let it worry you or freak you out. First, we start with a times b. So what is our a value? 3x. Oh, I'm so sorry. We start with a plus b. Here I go messing you up again. A plus b. So we're going to say 3x plus 2. Then we move on to a squared. A squared we said is 9x squared. Then we have minus a times b, which we said was 6x. And then we have plus b squared. And b squared is not 2 squared, it's 4. There we go. Nice and beautiful. Now let's use difference of cubes. Same thing, but this formula only has the negative in front here rather than over here. All right, so difference of cubes. You see the cube, we know we probably have to cube root it. What's the cube root of x cubed? It's x, so our a value is x. Cube root of 8 is 2. Now for a squared is just x squared. B squared is 2 squared, so 4. Next we have a times b, which is x times 2, so 2x. Now we're ready to write our formula. So we have a cubed, oh, right here, sorry, I'm looking at the wrong thing. A minus b, x minus 2, and a squared, which is x squared, plus ab. ab is 2x, so 2x, and plus b squared, which is 4. So, all right, difference of cubes again, last time. We need to cube root both terms. When we cube root 8, we get 2, and the cube root of x cubed is just x. B, when we cube root 64, I think it's 4. Let me double check. Yes, it is 4. All right, so a squared is going to be 2 squared times x squared. 2 squared, 4, and x squared is just x squared. Then we have b squared. 4 squared is 4 times 4 is 16. And last we need a times b, which is 2x and 8x. Now let's write our formula. A minus b. So we're starting with a, 2x, minus b, times a squared, which is 4x squared, plus ab, 8x, plus b squared, 16. There we go. Easy enough. Next section. Oh, and this is the last section. Yay, we're almost done. Okay. We need to multiply and divide these rational expressions. Let's start with this first one. Here we are multiplying. When we multiply, all we need to do is factor and then cancel things out and simplify. So here I see that this denominator can be factored, and I see that this quadratic can be factored as well. So factoring 10x plus 20, I ask myself, is 20 divisible by x? Sorry, not x, but by 10. 1 second. So 10x plus 20, is 20 divisible by 10? Yeah, it is. So we're going to take out a 10 and divide these by 10. 10x divided by 10 is x, and 20 divided by 10 is 2. So our factor right here is 10 times x plus 2. Now on the right we have a quadratic, and the quadratics can only be factored, not only, but in our cases, we factor them using ABC. So C goes at the top, B at the bottom. What factors of 3, what multiplies to 3? Only 1 times 3. Now we need to see if they add up to 4. Is 1 plus 3 4? Yeah. So our two factors here are x plus 1 and x plus 3. Now we can go ahead and look at our polynomial. Do any of these polynomial, oh my gosh, and our rational expression, do any of these factors match? We've got an x plus 3 and an x plus 2. What are we left with? I mean, we're not left with nothing in the top. When we cancel things out, if I said 4 divided by 4, 4 over 4, those cancel out, right? But we're not left with 0, are we? No. 4 divided by 4 is 1. So what if I said 2x over 2x squared? 2 and 2, those cancel out. We're left with x over x squared. But there's an x in the top and there's 2 x's in the bottom. So we're going to have another cancellation. I canceled it out. The x is going to cancel with one of the x's in the bottom. Does that mean we're left with just x? No, because the x is in the denominator. It doesn't magically become a numerator. It stays in the denominator. It doesn't mean 0 or nothing is in the top. We're left with a 1 in the top. A lot of people got that question wrong on the test. So here, back to our regular problem. We cancel out all these factors. That doesn't mean the top cancels to nothing. In the top, we are always left with 1. So our final answer here is 1 over 10 times x. Let's go to the next one. All right, here we have 20x plus 40. Is 40 divisible by 20? Yeah, it is. So we're going to take out a 20 and divide. 20x divided by 20 is x, and 40 divided by 20 is 2. Now on the bottom, we have a square and a perfect square. This is difference of squares. We just practiced those. We square root both of these. We're left with x. I'm so sorry. I said we just practiced those. We did not. We practiced difference of cubes. So it's okay. Difference of squares, we just square root both items. And we're left with a x minus 5 and an x plus 5. Now for this last one here, 5x plus 10. Is 10 divisible by 5? Yes. There we go. Because we're multiplying, we don't need any chicken with no keep change flip. So we go right into canceling. We got x minus 5, x minus 5, x plus 2, x plus 2. So what are we left with? 20 on top, 5 times x plus 5 in the bottom. But we are not done here yet. These coefficients, these whole numbers, can be simplified further. So we have 20 over 5. What is 20 divided by 5? 4. All right. Let's move on to the next one. Last two, dividing. We still need to factor this, 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 and this. Everything needs to get factored. So here, starting with our first numerator, we have a quadratic. So negative 8 on top, negative 2 on bottom. Factors of 8. 1 times 8, 2 times 4. Now, we're trying to multiply to a negative 8, so one of these numbers needs to be negative. If we have a positive 2 minus 4, we do get that negative 2 that we need. So we're going to have x plus 2, x minus 4. Next, 8x plus 24. Is 24 divisible by 8? Yeah, so we're going to divide these by 8. Take out the 8. We're left with x plus 3. Next numerator, 2x minus 8. Is 8 divisible by 2? Yeah, we take out the 2, divide by 2. And the bottom, we have another quadratic. 12 at the top, 7 at the bottom. 12, 3, and 4. Now 3 plus 4 is 7, so those are our two factors right there. X plus 3, x plus 4. Now, because we are dividing here, we need to keep, change, flip. This only happens when you divide. So we keep the first fraction exactly the same, change it to multiplication, and flip that last fraction. So let's just rewrite it nice and pretty. The first fraction the same. Change it to multiplication. and flip the last fraction. All right, now we can go ahead and cancel out any factors that match. I see an x plus 3 and an x minus 4. What are we left with? We have this in the top, this, and 8 times 2 in the bottom. So rewriting it, x plus 4 all over 8 times 2, which is 16. Last one, another divide, so we need to keep change flip. Kentucky Fried Chicken. Everything looks factored except for this denominator right here. This is difference of squares. So we square root both of these. We get x4, or sorry, x2. So we have an x plus 2 and x minus 2. Now keep change flip. We keep that first fraction, change to multiplication, and flip that last one. So here we have x plus 2 over x plus 2 minus 2. Change to multiplication, flip the last one. And now to cancel. We got x plus 2, x minus 2, and all we're left with is x minus 3 in the denominator. So that doesn't mean our answer is x plus 3. No, no, no. Our answer is 1 over x plus 3. Similar to how all whole numbers are over 1, all denominators are under 1. So even when there's nothing left and all you have left is a denominator, it is still a denominator. It's still in the bottom. And so that 1 stays on top. So our answer here is 1 x plus 3. Woo! 42 minutes and we are done. If you have any questions, ask me, ask your teacher, ask another teacher. Let me know if you have any questions for the exam. Good luck and happy Wednesday.